All right, so in this video, we're going to talk about endothermic and exothermic reactions. So first, we're going to talk about exothermic reactions. So there's a couple of key points of all exothermic reactions. Number one, products are more stable, have less potential energy than the reactants. Okay, heat is released overall. Heat is a product of the chemical reaction. And then lastly, delta H is negative, all right? Or the change of enthalpy is a negative change, all right? So let's look at an example chemical reactions where we could kind of see this. So here we see the reaction of the combustion of methane, where we have methane reacts with oxygen gas to form carbon dioxide and water. Now, granted, all combustion reactions are exothermic, but anyways, so as like I said earlier, well, heat is a product. And so oftentimes you may see that you will have some amount of heat that's been released in this reaction. And so if you see something like this in the product side where it gives you some numbers and some unit of heat on the product side, then you could rightly say, oh, this is it's an exothermic process. All right. Another way that you may see this, all right, is that sometimes next to the chemical reaction, it tells you something about the delta H. All right. Now they will tell you, remember, the delta H is just the change of enthalpy. In this case, this would be negative 213 kilocalories. So when you see that it's a negative number, this tells you also that this reaction is an exothermic process. All right, this is an exothermic chemical reaction, the combustion of methane. Okay, now you could also calculate this. All right, and I will show you exactly how this is done. So the heat of reaction can be calculated as the difference between the bond-dissociated energies in the products and the bond-dissociated energies of the reactants. So we could use this equation here to help us figure this out. So remember, the heat of reaction, or delta H, is the sum, all right, of the bond dissociation energy of the reactants minus the sum of the bond association energies of the products. So this is a way that we could figure out the delta H mathematically. Okay, and so you will need to use the bond dissociation energy charts, and then basically you're just going to look at each of those bonds, right, of your chemical, the chemicals that are being used in the chemical reactions, and then you will sum up all the reactants, you will sum up all the products, and you will take the difference between the two. Okay, and then that's how you figure out delta H. So let's go ahead and let's look at this example here with the combustion of methane. All right, so I'm going to go ahead and draw the Lewis structures of this. That way I think it'll be a little bit easier to see how we're coming up with these answers, coming up with the values I'm going to come up with. And so we have methane, which looks like this, all right? And it reacts with two oxygens, right, because the reaction is balanced. So two O2s to produce, we see that we produce carbon dioxide and water. And actually there's two of them. Okay. Now, what's important that we have to figure out how many of each type of bonds that we have, okay? And so for the CH4, if you notice, there are 4 CH bonds, all right? So the CH bonds, there's 4 of them, all right? For the oxygen, there are 2 double bond O's, all right? And so when we're thinking about this, there are 2 of these, okay? And then remember, we have to take the sum, okay? Now on the product side, if you look, there are 2 double bonded carbon oxygen bonds, okay? And so we have to take that into account, okay? And then when we're looking at for the water, you notice there are actually 4 OH bonds. 1, 2, 3, 4. All right, and so there are 4 OH bonds. Okay, And now essentially what you're going to do is that you will look at the bond dissociation energy charts like I showed you a little bit earlier. You look at that chart on a previous video, and then you will gather the values from there. All right. And so like, for example, in this case, for the reactant side, all right, it takes about 99 kilocalories per mole of energy in this case. So it will be 4 times 99. All right, plus, so we're looking for a delta H here, right? Plus, and we're going to put this all together. And then we're talking about for oxygen, all right, each double O bonds are 119 kilocalories, all right? And so basically it's 2 times 119, all right? Minus, all right, now we're going to look at the carbon double O. Now the carbon double O for this case, if you look at the chart, then you see is 191 kilocal per mole of energy, all right? And so I'm going to write 2 times 191 plus, and when we're paying attention for the oxygen, the OH, we see that for each OH is 112 kilocal per mole of energy that it takes to, that's a dissociation, bond dissociation energy for this particular bond. And so we're going to have 4 times 112. Okay. And so now we're going to kind of add these up. All right. And so 4 times 99, that gives us about 396. 2 times 119 is 238. And so we're going to add these two numbers together. When we add these two numbers together, we get that it is approximately 634 kilocalories. All right. On the other side, we have it that 2 times 191 is 382 kilocal, and 4 times 112 is 448 kilocal. And then so when we add this together, we get about 830 kilocalories of energy on the product side. And so essentially what you're going to do is delta H is equal to, in this case, is 634 kilocalories of energy. So that's how much energy it took to break all the bonds of the reactant side. All right, minus 830 kilocalories of energy. So this is how much energy that's associated with the making of all the bonds on the product side. And then so when you subtract those two, you see that we get overall negative 196 kilocal of energy. All right, so now we're going to explore endothermic reactions. So in the endothermic reaction, reactant are more the products. Reactants have less potential energy than the products, so thus they're more stable. Heat is absorbed. All right. Heat is a reactant in this case, and then your delta H is a positive number. Now let's go ahead and look at an example of this, right? Where you may have N2 gas reacts with O2 gas. In this case, this reaction requires 43, actually, let's change the units. This reaction requires 180 kilojoules of energy. And so that way you have 2NO gas. All right. And so, as I said, the one way to show that it's an endothermic process is that the amount of energy that is needed, you can see that in the reactant side. Or, other words, sometimes it will give you the delta H. In this case, because this is endothermic, this delta H will be a positive. So we have a positive 180 kilojoules. Okay. And so that's one way that, and that's other ways that we could kind of show endothermic process. And just like I showed you an example of the exothermic, where you could calculate what's the delta H of the reaction looking at the the bond dissociation energies, you could do the same thing here, and then you'll find that if you have a positive delta H, that the reaction overall is endothermic. Now, a couple of key points that you have to think about when it comes to heat transfers and chemical reactions, endothermic, exothermic processes. Number one, an exothermic process, remember, releases energy into the surroundings. All right, so thus a delta H it's a negative number. All right. Endothermic reactions, they absorb heat from the surroundings, so delta H is a positive. All right. Now, the reverse of an exothermic process is endothermic, and vice versa. The reverse of an endothermic process is exothermic. So if you kind of think about this reaction here, if I were to rewrite this reaction in the opposite direction, so 2NO gas produces N2 gas plus O2 gas, all right, plus 180 kilojoules of energy, delta H in this case would be a negative 180 kilojoules. All right, and so this process here, which is endothermic, if I write it the reverse, it's going to be an exothermic. All right, and you could definitely see that in the delta H. Now, the important thing that you need to keep in mind that the amount of heat absorbed or released in the reverse of a reaction is equal to that as released or absorbed in the forward reaction. The only difference is that the delta H has the opposite sign. All right, and so if this was going to forward, delta H is a positive. If you were to write the reverse reaction, or meaning you flip the reactants and products, then delta H will still be the same number, just the opposite sign. And that's some of the big thing that you just need to keep aware of. All right, so let's look at an example problem. And with this example problem, I want to emphasize several key points when it comes to delta H and how that relates to a chemical reaction. Okay, so let's look at this chemical reaction here. It says estimate the delta H in kilocal per mole for the reaction of hydrogen and oxygen to form water. Okay, so essentially we're looking for delta H of this synthesis reaction. All right, so the first thing we want to do, make sure we write out a reaction. And so we have H2 gas plus O2 gas to form water. So let's just assume water is liquid. All right, I guess that kind of works. All right, now we also want to make sure that our reaction is balanced. And so we need a 2 here and a 2 here. So our reaction is balanced in this case. All right, and so we're trying to figure out what's the delta H of this reaction here. And we could use the bond dissociation energies to help us figure this out. All right, but the first thing I'm going to do, I'm going to kind of draw out the Lewis structures so that we can kind of at least have a visual aid to help us to kind of figure out what bonds are being broken and what bonds are being made here. All right, so H2, we have 2 of these, right? For oxygen, all right, oxygen is a double bonded, and there's only 1, okay? And then it produces 2, we have 2 H2Os. All right, we're producing 2 of these. All right, and so when we kind of think about what type of bonds we have 2 of these, right? And plus we have 1 of these types of bonds. And then when we're considering what's our product, most importantly, our product consists of 4 of these. Since there's 2 H2Os, so we have 4 sets of OH bonds. Okay, and so now that we know that, we could look into a bond dissociated energy graph. All right, and it gives us the numbers that we need. So for H's, it tells us that the bond of H is 103 kilojoules, or kilocals, I'm sorry, wrong unit, kilocal per mole. For your double bond O's, it is 119 kilocal per mole. And then for our OH, it is 112 kilocal per mole. All right. And so our equation, if you recall, is delta H is equal to the sum of the bond energy, or bond dissociation, I'm sorry, energy of your reactants minus bond dissociation energy of your products. Oh, and these have to be the sum. Okay. And so now that we see what we see what we have, and so in this case we're adding this up. Oh, before we add this up, we gotta make sure we multiply this number by 2. This one's really just by 1, but this number is by 4. Okay. And so when we plug this in accordingly, we have delta H is equal to, in parentheses, essentially 2 times 103 plus 119, right, minus, in this parentheses here, we have 4 times 112. All right, and then when we plug this into the calculator accordingly and correctly, we get our answer to be negative 123 kilocal per mole. All right, so our delta H for this reaction is a negative 123 kilocals per mole. So what does that mean in this case? All right, so this means that, number one, that this reaction is overall exothermic. Okay, it releases energy to the surroundings. All right, ultimately, it releases energy to the surroundings. All right, if you were to rewrite this equation, and I'm going to rewrite it here, where we have 2H2 gas plus O2 gas yields 2H2O liquid, right? Since it's exothermic, you could essentially write plus 123 kilocals. All right, we could write that. Or we could say that the delta H is equal to negative 123 kilocal per mole. All right, we could write that as well. Both of them is equally correct. All right, you see that the kilocal is on the product side, so another indication that this is a exothermic process. All right, it being an exothermic process tells us that the potential energy of water is less than the sum of the potential energy of this hydrogen and oxygen. All right, so that's what this is also telling us as well. All right, now let's look at the delta H, change of enthalpy, and how does this relate to the chemical formula? Okay, and so this is telling us that it's you're producing a negative 123 kilocals per however moles of these reactants or products you get, right? And so what do I mean by this? Okay, so it's telling us that in this reaction, all right, if you have 2 moles of H2, all right, is going to produce negative 123 kilocals of energy, all right, in this reaction. It's also telling us that 1 mole of oxygen, all right, in this reaction, reacting 1 mole of oxygen according to this reaction is also going to produce a negative 123 kilocals of energy. Okay, creating 2 moles or producing 2 moles of H2O will produce negative 123 kilocals of energy. The point I'm trying to make here is that when you look at the stoichiometrical relationships or the mole-mole relationships between each of the reactants and products of the chemical reaction, depending on this number here tells us the number of moles that is needed or used, or whatever the case is, to have this much energy attached to it. whether it be a reactant, meaning that how much energy is needed for the process to take place, or a product, how much energy is released in that process as well. But the whole point is, because you have a 2 here, the mole ratio here is a 2 for H2. So for every 2 moles of H2 that you produce or that you use in this reaction, you're going to need negative 123 kilocalories of energy. All right. And on the same side here, if you were to have, like, for example, 4 moles of H2. All right. And so if you notice, I doubled my amount of moles. Okay. If you double the amount of moles, assuming that this is the limited reactant here, and then you have excess of oxygen, if you double the amount of moles of hydrogen, then you will double the amount of energy that's associated with it. And so in this case, instead of being negative 123 kilocalories, in this case it will be negative 246 kilocalories of energy that's associated with 4 moles of H2. All right. So what does that mean? Well, this simply means then you could figure out how much energy is used or produced or required based off maybe different number of moles of substances or mass of a substances that you have. Okay. And so let me give you an example. So let's just say for this particular reaction, okay, and I'm gonna kind of erase this here. For this particular reaction, let's say that you start off with 0.65 moles of H2. All right, and what you're trying to figure out essentially is how much heat is released during this reaction. All right, so the question that you're trying to answer is how much heat is being released. All right, so we could use the delta H here essentially as a conversion factor to help us to go from the number of moles of H2 to the amount of energy that is used in this reaction. Okay, and so let me kind of show exactly how that looks like. So you start with 0.65 moles of H2. Okay, now if we're looking at this reaction, we could clearly see that for every 2 moles of H2, you produce this amount of kilocalories of energy. All right, and we could use this as our conversion. Okay, where I would say 2 moles of H2. Where am I getting this 2 from? Here. It's coming straight from the chemical reaction. All right. And then I'm looking for energy, so I'm going to use this number here. All right, so that's my energy figure. In this case, it'll be negative 123 kilocal. All right, and so now what you just have to do is that you will have to actually put this in the calculator accordingly, and so that way we could ultimately get this answer. All right, so you have 0.65. You multiply that by 123, and then you'll divide that number by 2. Okay, and so when you do that, then what you'll find is that the answer to this question is about 40 kilocalories of energy, or negative specifically, negative 40 kilocalories of energy is released if you only have 0.65 moles of H2 to react with excess amount of O2. All right, so that's one way you could definitely look at this. Another way that this could be also be done is if they give you the mass. If I have given you the mass of hydrogen, then what you will have to do is just convert mass to moles, and then we could use a unit conversion or dimensional analysis to go from moles to the amount of energy using our delta H as that conversion factor.